So today I want to continue our discussion on sets. And I want to pick up from the last video in which we saw some simple examples, for example, this set, and we reasoned about the basic properties of sets and some of the notation and operations. And I want to go a little bit further. So for example, I want to introduce the set of what are called natural numbers, which I might write down like this: 0, 1, 2, 3, and so on. Now the difference between this notation and this notation, they're pretty similar. The only difference is that up here, I'm telling you this set contains exactly these three things. Whereas down here, I'm specifying what is in fact an infinite set. It contains infinitely many numbers, and so I can't write them all down explicitly. And instead I write down a few, and then I use the ... to indicate that you're supposed to continue that pattern. So this symbol n denotes this infinite set, which is the set of all natural numbers, all the whole numbers starting from 0 and going up. And in a similar way, I might specify what's written with this z notation and call the integers, using your intuition by writing ... -2, -1, 0, 1, 2. So the integers are meant to capture, again, only whole numbers, but now including the negative numbers, not just 0 and the positive numbers. So these are ways that I might write down infinite sets. I might try to present to you infinite sets that we want to reason about. Another infinite set that I might write down in a similar way would be, for example, 0, 2, 4, 6, ... I mean, and this seems like it's clearly meant to capture the ... seems to be continuing the pattern of taking the even numbers. And this leads to another notation which is very important in set theory, which is specifying a set by telling me what gets into that set according to some property that it has to satisfy. Like up here, the intuition is that I'm writing down here, I'm trying to indicate the set of all numbers, all the natural numbers that are even. And I can write that down in set theoretic notation as follows. So the way to read something like this, it uses the same curly brackets, but I'm not listing the elements of the set. I'm doing something different. I'm reading this as the set of all n and n, and this colon should be read as such that, and then finally I'm specifying a property which I could just read out and is even. So the way to read this is the set of all natural numbers n and n such that n is even. So it's a different notation, it still uses the curly brackets, but I'm picking out a set using a property instead of by explicitly listing the elements of that set. And this is also useful. It gives us a useful way of writing down, for example, some of the set theoretic operations that we looked at last time. In fact, both the ones we looked at last time. A intersection B can be written as the set of all x such that x is in A and x is in B. In other words, I'm specifying the property that an object x has to satisfy to belong to the set. The property is it has to be in A and it has to be in B, that property. And similarly, the property that an object has to satisfy to be in the union of A and B, this is the set of all x such that x is in A or x is in B. So we can capture the idea of intersection and union using the properties of conjunction and disjunction, or, with this notation. Now the last thing I want to talk about in this context is another set theoretic operation, complementation. So AC, this is read as the complement of A, or sometimes just A complement. So the C stands for complement. And the idea is this is supposed to be the set of all things not in A. But the problem with this conceptual definition is, what do you mean all things not in A? If, for example, I take A to be this set, this very simple set that contains these three numbers, what things count as not being in A? It seems pretty clear, you might think it's clear that 3 is an element in the complement of A. That seems intuitive, right? We missed 3 here. And 5 is an element in the complement of A. But what about 3.2? Is that an element in the complement of A? Is negative 16 an element in the complement of A? Is red an element in the complement of A? The point is, when you talk about complementation, you need to have a sort of background set in place with respect to which you're considering the complement. So this becomes maybe clearer when I draw the picture of what complementation is. I have my set A, and in the picture, the complement of A is supposed to be everything that's not in A. But what is this box? So it helps to have a bit of notation here. If I have two sets, A and B, and I write this little slash between them, this is meant to be the set of all x such that x is in A, but x is not in B. So this is sometimes read as A minus B, or A take away B. The idea is start with the set A and keep everything that's in A, but throw out anything that's also in B. So the picture of this, I've got A and I've got B. What are the points that are in A but not in B? It's this little crescent moon shaped in the picture that I drew. And now we can understand complementation as being a kind of minus operation where the thing that you're taking away from is implicit in the background. So we can look at the natural numbers take away the set 1, 2, 4 versus, for example, the integers take away the set 1, 2, 4. And now we get two different answers to the question of, is minus 16 in the complement? Here, minus 16 is not in this, because we're taking the complement on this side of 1, 2, 4 within the wider set of natural numbers. Negative 16 was never on the table. But over here, minus 16 is in the complement, because it was there to begin with in the set of integers, and when I take away the numbers 1, 2, 4, minus 16 is still left over. So now we've introduced the concept of set difference, and we've recognized that complementation is really implicitly dependent on a background set in which you're taking the complement, or with respect to which you're taking the complement.